Welcome back. Today we are looking at a few more concepts over electron configurations. Again, have your periodic table with you. The noble gas configuration was developed for use with the larger elements as a shorthand way of writing electron configurations. The noble gases are the elements in group 18 of the periodic table. So here they are over here. So let's take a look at the element strontium. Strontium is over here at number 38. So what you do is you go up one level on the periodic table, and then you go find the noble gas at the end of that period. And in this case, it is krypton. So you write the symbol for krypton in a square bracket. Then you go back to the level where your element is, or the period where it is, and you start writing the electron configuration as if you were starting at that point. So that is 5s, and we have 5s1, 2 for strontium. So 5s2, I have reached strontium and I can stop. Finally, let's do bismuth. Bismuth is over here, number 83. So I'm going to go one level up and I'm going to go to the end. Xenon is my noble gas, so I write xenon. Then I go back to the level where my element is, and it's period number 6 over here. And I start writing the electron configuration. So I have 6s2. Now you have to remember that after barium, we don't go straight to element number 71. We have to go to element number 57. And this is 4f. So 4f all the way through 4f14. Now I've reached 70 and I can go to 71 over here, and I go to the end of D. This is 5D, so 5D10. And then over here I have 2p, 3p, 4p, 5p, 6p, so 6p, 1, 2, 3. There are some exceptions to the Aufbau principle due to the fact that certain electron configurations end up being more stable than others, so this allows some elements to break the Aufbau order. A few things to consider here. A full sublevel of electrons, such as S with 2 electrons, D with 10 electrons, or P with 6 electrons, would be the most stable configuration. Then a half full sublevel, so S with 1 electron, D with 5, and P with 3 electrons would be the next most stable. And every other configuration is not as stable. Chromium and copper are 2 exceptions to the Aufbau principle. Chromium's electron configuration ends with 4s2, 3d4. So this is a full 4s sublevel and a neither full nor half full 3d sublevel. So one of the electrons from the 4s sublevel moves to the 3d sublevel so that we end up with 4s1 3d5, and here we have 2 half-full sublevels, which is more stable than the original Aufbau prediction. Similarly for copper, copper's electron configuration ends in 4s2 3d9. So again, we have a full 4s sublevel, but neither full nor half-full 3d sublevel. So again, one of the 4s electrons moves to the 3d sublevel, and we end up with 4s1 3d10 for copper. So this time we have a half full and a completely full sublevel for 4s1 and 3d10 respectively. This is more stable than the predicted configuration. There are many more exceptions, but these are the 2 you need to know. We talked about ground state and excited state electrons before, and we even did the flame test to experience it. So now let's look at what happens to electron configurations when an electron becomes excited. So we'll take potassium as an example. The ground state electron configuration for potassium is shown over here, and it ends with 4s1. So when an atom of potassium is subjected to a source of energy such as heat or any other source of energy, an electron can go from its ground state to an excited state electron configuration. So what happens? An electron can jump to a higher energy level, and that could be any level higher than 4s1. So if we look at the periodic table, 4s1 and potassium is over here. So that electron could jump anywhere, somewhere here, somewhere in the 4p, somewhere in the 4d, in the 5p, and so on and so on, as long as it is higher than the 4s1 level on the F-bar order. So an excited state electron configuration for potassium could be 3p6 and then 5s1, let's say, or 6p3 or 7s2, etc. So how do we know that this electron configuration would still reflect potassium? Well, all we do is count the electrons. We know that potassium has an atomic number of 19, so it should have 19 electrons. And as long as we have 19 electrons, it is still potassium, just in either the ground state ending at 4s1 or the excited state if that electron has moved to a higher energy level. Hope you have taken good notes, and see you in class.